All right, lesson 2, the limit of a function. So, recall from last class what we were doing, that we were figuring out the slope at any given point, right? So we said if we had a curve, right? So let's say we had like this curve, and we wanted to figure out the slope at like maybe 3 on that curve. What we would do is we would get closer and closer to 3 to approximate what the slope was, right? So we'd have to use the secant lines, right? So we go from this point to this point, figure out the slope, and then get a little closer, and the slope gets steeper. And we go from the left and we go from the right, right, to make that work out, to figure out what the slope was. And we'd say that the slope was approaching, right, some number at that point. That was actually called, like, there was another name for that. It was approaching the limit at that point, the limit for the slope at that point, right? So we can say last time, we've already kind of done a little bit of this, where we were figuring out the limit of the slope of the secant line. Okay, so now we're going to be doing kind of more with that, where we're going to be approaching a number. So what is a limit? Okay, the limit can be described, or it's used to describe the value that a function or sequence approaches as the input value approaches a particular given value. Okay, what do I mean by that? Before I maybe explain this down here, I'm just going to show you like with a little graph here. Being all fancy now, I've got these little gizmos here in here that aren't going to work. So if we were looking, let's say, at this function, whatever it is, right? Then when we're talking about the limit of something, is let's say, like, let's look at the point 3 there, right there, right? So this point on that one. Well, we can see that as we approach that point, then the value of y is getting closer and closer to what value? 2. It's getting closer and closer to 2, right? And that'd actually be the same on the other side, right? So as we get closer and closer to 3, my x value of 3 from the right, then again, it's approaching 2, right? So that's what the limit as x approaches 3 would be. It would be 2, right? So not a big concept, right? It's just like as you get closer and closer, like what number is it getting closer and closer to, right? But just so you can see, well, actually this would be a bad example, but I'll show you some other examples where it just won't be quite so obvious here in a minute. But here is the notation. So you guys haven't really seen this before. You're gonna be doing a lot here in a bit. And the way we would say this would be the limit of f of x as x, and then the arrow means approaches a. So that would be like some number. You'd put like approaches like, 3 in the last example, or whatever it might be. And then L, that's really going to be like your y value. That's like your output. Yeah? All right. So to find the limit of a function as it approaches most points, you're probably thinking this anyway, right? What we can usually do, why don't we just throw a number in for x and see what we get out for y? Wouldn't that be the same thing, right? Just put a number in and get one out for the output. So that would be true in this case, right? It would be true to say, if I said, what's the limit of the square root of x as x approaches 16? We should just be able to say, okay, the limit as x approaches 16, and we can just throw in 16 in for x. Okay, so the limit as x approaches 16, so the limit as x approaches 16 of f of x, I guess you would say, would be equal to 4. Did I forget anything there, though, with the... Yeah, there's that whole thing, right? It could be plus or minus 4, right, when you take the square root. Those are always tricky. Okay, so let's do another one. So, the limit... Here, I'll just leave it like that. So again, we can just throw that number in, right? Let's see what we get. So if we go 1 minus 2 times negative 3 minus negative 3 squared over 4 times negative 3. Okay, then this would be 1 plus 6 minus 9 over negative 12. So this would be 1 over 6 in the end. So this shouldn't really seem like anything. What's that? Oh, I skipped a step there, yeah. In the end, it would end up being 1 over 6. Yeah. Okay, so in the end here, this probably doesn't seem like rocket science, does it? Like we're just kind of plugging in numbers like we've always done into a function, right, to get a number out. And that would be the case. Like it should, if we have what's called a continuous function, then that always would be the case. We can just kind of plug that in to see what we get out. But now, so functions with the property of the limit as f of x approaches, or as x approaches a, is equal to f of a. Okay, let's just see if we can make sense of that too. This is saying the limit as f of x, or of f of x, as x approaches some value, right? Let's actually put a number in there to make sense of this. So this would be like the limit of f of x as x approaches, let's call it 2 for a second, just to kind of make sense of this, should be equal to f of 2. That's really what we were just doing, wasn't it? Right? Because if we throw some number like 2 in, then we would get, well, f of 2 is the y value at 2, when x is 2, right? That's all that's saying, right? Even though this looks all fancy. So anyway, it says, functions with the property, the limit of f of x as x approaches a is equal to f of a, as the examples above. They're called continuous. Nope. So they're called continuous at a. So in the next lesson, we're going to be doing a lot more with continuity and continuous functions. But yeah, for the most part, you just plug them in, right? But now, let's see what the problem is going to be and where they become a little bit more difficult. So if we had this example, it says if f of x is equal to x squared minus 9 over x minus 3, then determine the limit as x approaches 3 of f of x. Okay, so let's try the thing we just did there, right? So if I put in 3 in this, then that would be 3 squared minus 9, that would be 0. And then 3 minus 3 is 0. Right? So I'm getting something that's called a indeterminate, right? That's an indeterminate form, right? So that means that it doesn't mean that there isn't a limit there. It just means that it's indeterminate right now. I don't really know what the answer is for this yet, right? So we have to do a little bit of algebra just to figure these ones out, okay? So let's take a look at the graph that we were just looking at there of f of x for a second, right? So if we so if we were to graph this, it would look like this. So at 3, we'd be up at 6, and then there, and so on, right? So this graph would look like this if you put it in your calculator. And what do we have going on at 3? Yeah, it's a point of discontinuity right there, right? But then if we kind of think about this for a second, would we be able to figure out the limit at 3 though? Like if I'm looking at this right now, right? So you can see from the left side, as this thing is going farther and farther to the right, like right as it's going this way, what number is it approaching? Because that's what we're talking about when we're talking about a limit. What number is it getting closer and closer to? Yeah, it's getting closer. As we get closer and closer to 3, my y value is getting closer and closer to 6, right? And then the same thing from the other side. Like we're getting closer and closer there, right? So looking at the way the graph is right now, what would the limit, what should this be? It should be 6. Even though that's not a point on the graph, right? The limit can still exist, even though there's not a point on the graph for that limit, right? So, okay. So in this case, it says f of 3 is undefined, but the limit, so the limit of this, which we said was probably 6, right? We'll kind of do this in a minute, is not equal to f of 3, right? They're not equal to each other, so just be careful on those. And we'd also say f of x is discontinuous at x is equal to 3. It just means that it's like broken, right? So when you're thinking of like a continuous graph, it's pretty much like you can put your pen down and draw a line and then not take your pen off, right? That would be a continuous graph. Okay, so now let's do that same thing algebraically. So if we were to do this algebraically, what we would want to do is we would want to take our original function, x squared minus 9 over x minus 3. Right, and let's do this right. Let's actually write out the limit as x approaches 3 of this. Okay, any ideas on what we should probably do to figure this out? Yeah, let's factor the top. Let's see what we get when we do that. So again, this is technically what you should be doing. You should be writing the limit as x approaches 3 along the side every time. And I know it's annoying, and you'll probably take some shortcuts along the way, but that's technically what should be happening every time we do this, right? So let's factor the top, right? So this is the difference of squares. So this would be x minus 3, x plus 3 over x minus 3. And then look at this. We can cancel that now, right? X minus 3 and x minus 3. So those are good to cancel. So now our expression becomes, what is the limit as x approaches 3 of x plus 3? 6. Right? I can see that now, right? I can actually just throw 3 in for x and say, okay, well, that would be 6. Right? So this is going to be the idea when we're doing these questions. When you get a situation where when you put in the value of a into your function and you get a 0 over 0 situation, you're going to have to cancel something, right? You're going to be messing around with it mathematically in order to cancel something. And usually when you cancel that something, it's going to work out. And then you'll be able to put it in. Okay. So in this one, okay, so for the first one here, says... Okay, so on this one, we got x to the power of 3 minus 8. And I think I got to factor something. Do you guys know how to factor that one? This wasn't part of 30-1, right? Like we didn't really do these ones. Do you remember that new thing in your when you're going through that? Yeah, I'm gonna write it out just so we can see it here. It's a cubed minus b cubed is equal to, and then it's a minus b, and then a squared plus ab plus b squared. All right, that's the form that we're wanting to put that top one in. So let's figure out, well here, I'm just gonna write it one more time. So we've got, this is x to the power of 3 minus, and then this 8, what I need to figure out what b is here, right? So I'm just gonna write this a little different. I'm gonna write this as 2 to the power of 3 so I can kind of clearly see what my b value is. And then if you need to, just make sure that we get this right. Let's write down, so my a value is x, right? And my b value is 2. Okay. So from there, we should be, well here, I'll write the whole thing. So this is over x squared minus 3x plus 2. And then we'll factor the top now. So the top here would be the same thing as x minus 2, right? Just a minus b. And then times x squared plus 2x plus 4, right? Because that's 2 squared for the last one. Okay, so there. That's the factored version of that difference of cubes. Over. And then on the bottom, you guys have been factoring those forever, right? That's going to be x minus 2 and x minus 1. So, perfect, right? Like I was saying, we pretty much want to cancel something. So this one kind of lined up nice. X minus 2 cancel. So now let's take the limit of that, right? So let's take the limit as x approaches 2 of x squared plus 2x plus 4 over x minus 1. I can already see that this one's going to work out better. Maybe I should have said that from the beginning too, guys. Sorry. Right from the beginning, what we should have done is we should have checked to see if it would have worked just from the get-go, right? And if you did, what you would have seen is that we would have had 2 cubed minus 8 is 0. And then if I would have thrown 2 into here, again, it would have been 0 over 0, right? So that's why we're doing this, right? Just because we need to get a different situation happening. Okay, so now if I throw that in, you end up getting 12. Are you guys good with that part? Just throwing 2's in for the x? Okay. All right. Next one. Complex fractions. So this is another style that comes up quite a lot in calculus. You guys are going to be doing a ton of these ones. So we've got the limit, going on there. Just check again. If I throw 5 in for x, I'm dividing by 0. This isn't going to work, right? It actually ends up being 0 over 0, right? 1/5 minus a fifth. So what can we do? Well, I'm just going to write it out one more time. So this is 1 over x minus 1 over 5 over, and then x minus 5. I didn't change anything. I just kind of wrote it out by itself there. And again, I'm being lazy here, but I should be writing the limit as x approaches 5 on the left. All right. I don't like this complex fraction going on at the top, right? So I'd like to get rid of that. I'd like to cancel something. Where would be a good place to start? Yeah.
You multiply the 1 by 5 and the other by or yeah, I can't remember.
Cross multiply the fraction.
Perfect. Yeah. Yeah. So we're looking at the top here, right? I'd like to just write that all over one common denominator, right? So if you did that, technically what you'd be doing is you'd be multiplying this side by 5 on the top and 5 on the bottom, right? And this side by x and x. But either way, in the end here, you would end up having, here, I'll write it. I'll write out the middle steps too. This would be 5 over 5x minus x over 5x over, and then this is all over x minus 5. And then this is where I'm going to combine it over a common denominator. You guys are going to be doing so much, you're probably going to, you wouldn't have written down or wrote down that middle step. If you want to, great. So this would be 5 minus x all over 5x. And then that is all over x minus 5. Now again, just to keep yourself from getting confused on these ones too, I kind of like leaving the brackets on there just to remind myself that was the top fraction, right? And then this is the bottom fraction. The other one that's common to do is to leave this line longer than the other line. Kind of just helps keep it organized in your head. It should all work out either way, but this just helps to think about it. Okay, so then what would you do from here? Yeah, because this is really x minus 5 over 1, right? You can think of it that way. So then in the end, you could rewrite this as 5 minus x over 5x, and then divided by the reciprocal, right? Or, sorry, multiply by the reciprocal of that. So that would be 1 over, and then x minus 5. Well, that's not quite right. What do we got to do here?
Take minus 1 common.
Perfect. This is that tricky little situation where it looks like I should be able to cancel those, right? But they're not exactly the same. So our little trick here, you could do it out of either. I could factor a -1 out of the bottom, or I could factor a -1 out of the top, and we'll see what happens when we do that. So if we factor the -1 out of the top there, that would be -1 times, and then now this would be -5 plus x. And then that's perfect, isn't it? -5 plus x is the same thing as x minus 5. So good to go. And then over 5x times 1 over x minus 5. And then now those are good to cancel, right? Okay, and then just in the end here, just writing it all out, we've got -1 over 5x. Now I did that. What do I have to do now? What was the whole point of this? Right, we were trying to figure out the limit at this point, right? So I should have been writing it at every step, but I'm going to write it again here now. The limit as x approaches 5. So I can throw 5 into that now, and it's not going to give me a 0 over 0, right? So that would be -1 over 5 times 5, so -1 over 25. Okay. Now, how would you figure out at that, that's the limit? Maybe this would be this isn't the question, but what would the point on the graph be? Exactly. Yeah. So if we were looking for the point, if it said what is the point on the graph, what is f of 5, or no, it would just be the point on the graph, and the point of discontinuity in this case would be the point, the x value, right? 5, comma, -1 over 25. Yeah. They just happen to be the same number. In this case, this is f of a or f of 5, and this was the limit. But they were the same this time, but they wouldn't always be the same. Okay. The next common style with radicals. You guys probably bringing up old memories, eh? We did a lot of this stuff in 20-1. What do you guys think you'd do here? Any kind of general strategy that you do to solve this one? Yeah, we could rationalize the denominator on this one, right? That'd be a good place to start, right? I got nothing else I can even try, so let's do that one. So, how do you rationalize the denominator again? So I got to get that square root out of the bottom. Do you guys remember what I multiplied by to get rid of that? There's a fancy name for it too. Yeah, good. Yeah, conjugate pair. Yeah, the conjugate of this. Yeah. So we're going to multiply this by the square root of x plus 2, right? That's the conjugate pair. But I can't just multiply the denominator by that, right? So we also have to multiply the numerator by the same thing. Square root of x plus 2. Okay. Now, I'm going to leave the top for a second as just x minus 4. And then square root of x plus 2. I'll explain in a minute why I'm not distributing that out like we might. And then the bottom. Do you guys know what the bottom would be looking at that one? Why the conjugate pair even worked? Can you see what the answer would be just from looking at that one? What would it be? X minus 4, yeah. Oh yeah, that's right, good. Yeah, so x minus 4. Now, do you guys see now why I didn't expand the top? Yeah, you might have messed yourself up there, right? Because you wouldn't be able to cancel anything. So in this case, I left the top just like that because I want to cancel something. So it's just in my best interest not to expand that one out. So then at this point, perfect. As soon as you cancel it out, you're like 99% sure that you did it right. As soon as you cancel anything. Okay, and then now we can throw it in, right? So now we can say, okay, the limit as x approaches 4 of, and then all we have left is the square root of x plus 2. Would be, so then that would be equal to 4. Yeah, you know what? We're actually gonna do a different one. We're gonna be doing tons of ones like this, but I think just for now, let's do a different one. Let's say the question was this: the limit as x approaches -1 of x minus 1 over x squared minus 1. Okay, I'm going to pause it and... Alright guys, so if you're watching the video too, if you're confused, that's probably for a good reason. So once you get to this point, right, if you say, okay, I've canceled these out, right, I factored that top and canceled them, then you'd end up with the limit as x approaches -1 of 1 over x plus 1. Do you guys see what the issue is here? The limit would be 1 over, if I throw a -1 in for x, that's -1 over 0, or sorry, 1 over 0, right? So now this isn't actually not an indeterminate form anymore. This isn't that we don't know what the answer is. We actually do know now. The answer to this is actually undefined. So you'd actually say undefined or does not exist. DNE, especially in my open math, that's the way it's, if that was the answer, that's what you'd put in. Okay, so what's actually happening there? Well, just think about that graph for a second. 1 over x plus 1, right? So 1 over x plus 1. This thing would have a horizontal asymptote where? At -1, right? Right where we're trying to find the limit of this thing, right? And if you remember back, our rational graphs, like for this one, would be on this side, and then it would also be on this side. that kind of makes sense, right? If I'm saying like what number for y does this thing approach? Well, it looks like approach is like infinity, and it also approaches negative infinity at the same time. So this doesn't actually make any sense, right? So this is a situation where it doesn't actually work out. Okay, last one. And actually, you know what? This question is almost identical to the other one, so I'm actually going to skip this last one.